Hello everybody, this is Dr. Ali Mughebel, and we're covering Nyquist criteria for Zero ISI. The outline of the presentation goes like this. We'll start with the intersymbol interference, then we'll go on to Nyquist criteria, and what do we do in terms of pulse shaping to account for Zero ISI. Intersymbol interference. Given a pulse shape, how can it be used to transmit M-ary forms? We can use discrete pulse modulation, and we can vary the amplitude, duration, or pulse position to represent the M-ary in a discrete manner. The problem is that we get intersymbol interference when communication channel is dispersive, which means it has a certain limited bandwidth. The bandwidth is less than the bandwidth of the signal that we want to transmit. And once the pulse go through dispersion, it means they will expand in time, and that will cause error. Pulses will interfere with each other, and that's what we see in baseband pulse transmission. Now let's assume that we will be dealing with pulse amplitude modulation, which means the data is represented in the amplitude. We're starting by a binary sequence which is taking 0 and 1. We'll refer to this with blue BK. To be consistent, we will use green AK to represent the polar representation. So if you start with BK, the original source of binary sequence, once we convert that into polar representation 0 and 1, we'll call that AK. Let's see in the following diagram. So we start with the source, binary data source here, and then we go through the pulse modulator, amplitude modulator, which we adjust the amplitude being we will look at the pulse amplitude modulator that will take positive or negative, and then we get AK, which AK goes into the transmit filter. So here we have the sequence. We can convert that into different amplitudes, whether binary or otherwise. We have AK, and then we pulse shape that, which is the pulse transmission filter. We go through the channel. Additive white Gaussian noise will be added, and we assume we have an optimal filter. Because we'd just like to focus on intersymbol interference, we'll assume that we have an optimal way of dealing with the white noise. We have two problems, ISI, because of the band limitation of the channel, and we also have noise. But as I said, we'll focus on the ISI, assume that the filter here is matched to the noise. Then we have, of course, the sampling time, because we are dealing with digital communication. And then we have the decision device. We have a threshold that we compare with. All right. Now, this is the block diagram we have seen before. So the transmitted sequence will be, in fact, sum of all possible pulse shapes. So we're summing from k minus infinity to infinity. With the pulse shape, of course, the pulse will be delayed at multiples of the bit duration, and will be scaled by the proper amplitude. That's what we get as S of t. Now, at the receiver side, we will get the pulse shape after the matched filter. So P is the result of going through the channel and the matched filter. This pulse shape will be adjusted by the channel and will be adjusted by the received filter. So this is why we don't get GT here, we get P. We also have the scaling factor for the signal, and we have also the noise. The noise, N of t, it's the white noise after going through the filter. We call it N of t. Now, we mentioned that P is nothing but the convolution of the original waveform with the channel, and then we have the receive filter. H is the impulse response of the channel. C is the impulse response of the receive filter. In the frequency domain, we can convert the convolution into multiplication. Now, we also mentioned that N is a result of the white noise through the matched filter. So the white noise is Gaussian with zero mean and power spectral density of N naught over 2. After sampling, we get Y of t. I'm using green color here to show you. Then instead of small t, which is valid at any time, would be using multiples of capital TB. So we have I, integer multiples of TB, because this switch will be sampled at multiples of the pulse duration or the bit duration. So basically these are similar equations, but instead of small t, we use I times capital T. Now, if you look at this expression and we try to expand it, we can take one of the items here. So we're saying when k equal to I, when we are at the bit of interest, we get one waveform outside the integration, because you get I and k are equal, so this is going to give you the pulse at 0. We assume it's normalized, so we get AI outside, which means that when I sample, I will get the exact shape or amplitude that I'm looking for. That's the data I'm looking for, but it will also be added to other components, pulses before and after. And of course, we'll have the noise at that instant of time. So this is what we want, and this is the unwanted. This is the green, the good part of the signal, and this is the unwanted signal. I am coloring this in red. This is called the ISI. It's always there unless we deal with it. So the unavoidable presence of ISI and noise in the term introduces error in the decision, because this is a signal and this is all can be considered as noise. So in the design of transmit and receive filter, the objective is to minimize the effect of noise and ISI. We would like to deliver the digital data to the destination with the least possible error as possible. If the signal to noise ratio is high, the operation of the communication system will be limited by ISI. If the signal relative to the noise is high, then the only problem we'll have will be ISI. The noise term will be neglected in the signal to noise ratio. However, otherwise, we'll have to deal with noise. Techniques to control ISI in higher signal to noise ratio determine the pulse waveform for which ISI is eliminated. So we are looking at pulse design. We'll assume that we have no problem with the noise and would like to get rid of ISI. And that's called pulse shaping. Now, Nyquist criteria for the distortionless bandpass transmission. Nyquist came up with a criteria for distortionless baseband transmission. Transmission function of channel and transmitted pulse shape are specified, and we need to determine the transfer function of the transmit and receive filter to reconstruct the original data. Our objective is to reconstruct the original data. The pulses, the channel is given, the transmitted pulse is given, and we need to come up with the original data. So we need to control the overlap between the pulses. It would be great if we make the overlap equal to 0 between all other pulses, and of course 1 if we deal with the pulse itself. This is the condition in time, and if it's satisfied, then the received output would be as required. I'm trying to put a figure here that reflects this. So all these waveforms have 0 ISI because the contribution would be 0 from other pulses. So that in that case you get Y equal to AI for all possible I's, which means that we got rid of the ISI, which is called 0 ISI. Although there is overlap, but this overlap crosses 0 at the point of interest. Now let's try to derive although we have done that before. If you visit my other course, Communication Engineering, you'll find out that we have some derivation of Nyquist criteria. We'll do it just quickly here for the sake of recall, although the derivation is done a different way, but the principle remains the same. Consider the sequence of samples and recall the sampling in time results. Consider this sequence of samples and remember that sampling in time results in periodic function in the frequency domain. So we can say that the Fourier transform of infinite periodic sequence of pulses will be periodic. So the Fourier transform of those pulses will be periodic. Remember that RP is the sampling rate, or if the transmission rate, it's the bit rate, assuming binary, and it's equal to 1 over TB. So if you take the Fourier transform of the pulse. Okay, you take, if you want to get the Fourier transform of the pulse, you can start with sampling at the instant of interest. So we're just taking one sample. This is a sampling of the original pulse, should equal to the spectrum here. So the red one is in the time domain. If you want to get 0 ISI, then as we mentioned, that this summation should equal to 1 or 0 otherwise. 1 if they are equal and 0 if they are not equal. So basically this summation reduces to one single pulse at the time of interest, and we got just one delta multiplied by exponential, and that's the Fourier transform should equal to 1. Taking it one step further, this is the Fourier transform should be constant, and replacing RB with 1 over TB, multiplying both sides with TB. So we can say that if you sum the spectrum of the pulse of interest and shift it to the right and left at multiples of the transmission rate, you should get a constant. It doesn't have to be TB, by the way, it could be any constant, but let's say TB. So I'd like you to remember this formula. This is called Nyquist criteria in the frequency domain, and we'll get some examples, we'll talk about it. Okay, so for example, if you look at the following waveform, okay, recall that the spectrum of the pulse that we want is not the transmitted pulse, but rather the pulse that is received, which makes things difficult because I can easily control the transmitted G, but then I have to make sure that the overall is 0 ISI. So it's the P that we are interested in should be the cascade of all three: the pulse, the channel, and the received filter. Okay, so if this is the case, then we want PF to be 0 outside and 1 here in the middle. The question is, can we get 0 ISI? And the answer is yes. The simplest way to satisfy the condition is to use a Richt function. This Richt function, if shifted to the right and to the left, we can have a constant, and of course the Richt will translate in frequency into a sync in time. So Richt in frequency will be sync in time. So we're saying if you send sync, then it's possible that you get 0 ISI because the next sync will be here. I'll show you in the next graph. So this diagram shows you a sequence of ones and zeros. Although pulses smear, they overlap. At the point of interest, they give you 0. The special case of the bit rate equal to 2W is called the Nyquist rate. If you transmit at exactly twice W, then you can get 0 ISI. We have ideal bandpass pulse transmission, in the frequency domain, and as an equation for in frequency domain, the ideal channel, we have an ideal Nyquist channel. Ideal Nyquist achieves economy in bandwidth because this is the minimum possible bandwidth that you need, which is bandwidth equal to RB over 2. The bandwidth is half the rate in binary. It solves the problem with 0 ISI with minimum possible bandwidth. There are two practical difficulties with using sync. Of course, sync start at minus infinity to plus infinity, which means that you have to approximate sync. You cannot have sync in real life. Also, the decay factor of sync is 1 over T, which means that if you have error in timing, so if, for example, instead of you sample here, you sample on the side, you will get some ISI. I would love to have a smaller tail. So because if I do a mistake, then the impact of the mistake will be less. So two problems with sync. They are not physically realizable because they have infinite time, but we can approximate. The second thing is that their decay rate is not as good as other pulse waveforms, as we're going to see. Then we're going to move next to the raised cosine, where we say, is it possible to trade off some bandwidth for quality? I will just use more bandwidth or use less rate and reduce the tail, the exact timing requirement. So I'm showing you 3 examples. This is the one that we started with. The Richt in frequency give you sync. Then as you start to increase, okay, 50% of the bandwidth, you get the following waveform. So the tail become less, and as you go to the double the requirement, RB equal to RB, the rate equal to the bandwidth, you get very small tail, and also you have additional zero crossings here. So we can summarize that case 2, if the bit rate is going to be less than twice the transmission bandwidth, we may overcome the practical difficulties encountered with ideal Nyquist channels. By extending the bandwidth, we're going from W to 2W, and we can define the transmission bandwidth to be W times 1 plus alpha. Of course, if we have passband or baseband, there will be a factor of 2. So if alpha equal to 0 or alpha equal to 1, we can get 2W, and the minimum is going to be W. We can have divide by 2. This is in case of passband transmission. We can have also baseband transmission. Alpha is called the rolloff factor. Some textbooks they use R. It's basically how much extra bandwidth you have relative to the excess bandwidth is how much extra bandwidth you have relative to W. So in case we can have different transmission, different ways of defining it. So if F1, which is the extra bandwidth relative to the original, so that's called F1, then we can claim that the bandwidth requirement is less. All right, so we look at the raised cosine. The raised cosine has 3 distinct regions. The one in blue, which is a constant, and then we have a transition. Fx is the amount of extra or excess bandwidth. So the bandwidth is extended from the minimum RB over 2 to RB over 2 plus Fx. By symmetry here, we have RB over 2 minus Fx. So we have 3 regions, blue, and then we have the red region, and then we have the zero region. That's the general definition of the raised cosine family. Now, the raised cosine satisfies the Nyquist criteria because if you take this waveform and shift it to the right and to the left at multiples of W or multiples of the sampling frequency, you get a constant. If you keep adding to the right and to the left, and that, of course, region, you get a constant amplitude which satisfies Nyquist criteria. Now consider the extreme case of full rolloff factor raised cosine. Raised cosine itself is a family of curves. As you can see here, all these colors are part of the family, but with different values of excess bandwidth or different values of rolloff factor beta or R. So in this slide, we consider the full rolloff factor raised cosine, where we extend the bandwidth to the maximum. And then in that case, we can simplify the expression because there is no constant now. Everything is now just a transition. In the time domain, we can simplify the expression by taking the inverse Fourier transform. And this is exactly the full rolloff factor raised cosine in time domain. Now, the advantage of this specific scenario of full rolloff factor is we have faster delay. You can see here that this is equivalent to the green signal. Bandwidth is more, but we have fast decay, sorry. So the decay is small. We also have 2 more features. At half of the duration, we get exactly half the value. So at t equal to tb over 2, we'll get half the value of the pulse itself will be half of the maximum amplitude. Okay, here we have 1, here we have only half, or exactly half. Now, also we notice here that we have an additional zero crossing here in between, if you zoom in. So there are zeros crossing at these points, at these exact points. We have additional zero crossing in between. Now, those 2 features are proven to be very relevant, very important when it comes to synchronization. So in total, we have 3 features for the full rolloff factor. Faster decay, we know the values at half the period, and also we have additional transitions, zero crossings, and that's very good for synchronization. Now, of course, for these advantages, the price paid is clear compared with alpha equal to 0. This is alpha equal to 1. The price is double the bandwidth requirement. So the price is use of channel bandwidth compared, or double that compared with ideal Nyquist channel. Now in this slide, I'm just quickly summarizing the two extreme scenarios. Those are family members of the raised cosine. These are the two extremes. We have rect, which translate into sinc, or we have the full rolloff factor. Okay, now we just want to highlight that it's not as easy to design for very exact pulse shape, because this pulse shape is required at the receiver side, not at the transmitter side. So even if you design it at the transmitter, it might change on the way. So the bandwidth requirement, this is one of the very important formulas you need to solve for the data rate. We have the bandwidth is the minimum bandwidth plus additional bandwidth, excess bandwidth, which is RB over 2 is the minimum plus alpha RB over 2. If we are using sync pulses, this is going to be 0. Okay, remember that alpha or R, the rolloff factor, is how much bandwidth extra relative to the minimum required bandwidth. This is the case for baseband transmission. If we have passband, remember that the factor of 2 will disappear. Now let's conclude with some examples. Choose the correct answer. Compared to a sync pulse, the raised cosine pulse with rolloff factor alpha equal 1 has the following advantage: A, B, C, D, E. Mark your answer in the comment section. The second multiple choice question says data at a rate of 7 kilobits per second is to be transmitted over a baseband channel of bandwidth 4 kilohertz. So we're given the data rate, we're given the bandwidth. Using binary Nyquist criteria pulses, determine the maximum value of the rolloff factor alpha that can be used. A, B, C, D, E. Mark your answer. Question 2. Now, we have two waveforms. One is blue and one is red. One was drawn with alpha equal to 0.2, the rolloff factor, and one was drawn with higher rolloff factor of 0.5. The question is which is which? You can zoom in and think about it. Which one of these two is alpha equal to 0.2 and which one is alpha equal to 0.5? You can relate to the color. So 0.2 is which color, 0.5 is which color. The last question is it possible to design a system with zero ISI and separate greater than twice the bandwidth? Justify your answer in view of Nyquist zero ISI criteria. You can have some sketch to show your proof. Is it possible or not? And then justify. Thank you, and we'll see you in coming videos.